Okay, we are starting a new lecture today, and that is on root finding. This is actually the first time. All right, spring break is over. Chameleon, spring break is over. Hi, welcome. All right, so we're starting a new lecture, and this is actually our first lecture on a numerical method. Okay, so far we've just been basically putting together our toolboxes that will help us actually solve a problem. Okay, so everything else so far has been a preparation. Linear algebra was essentially preparation in data management and how to manage data on computers. Then also discussing errors that you can have in storing the numbers. That's again a preparatory step. And our introduction to programming was our tool to actually do that using computers. So we will continue working both problems a little by hand, so because you have to know the procedure, as well as using computers. So that part is the same. So without further ado, let's get going. I do think I posted the lecture just before now, so you can download PDF of this presentation as well. So root finding. Again, we have done all of our preparatory steps and we are ready to go. Here's one very common problem in petroleum engineering, and that is figuring out what are fluids doing at high pressure and high temperature. To give you some idea of how high of a pressure or high of a temperature, let me ask you a question. As I go 1 kilometer down into the subsurface, how does my fluid stress, fluid pressure change? How much does it go up per kilometer? 10 megapascals, or 0.44 psi per foot. So that there are two numbers, basically the gradient of pressure. As you go down, you have basically a whole lot of weight on top of you, as well as things squeezing you from the sides as you go deeper. And that results in fluid pressure that goes 0.44 psi per foot, or 10 megapascals per kilometer. Overall stress, that's just fluids. However, we have every rock is filled with fluids, and that assumes that those fluids are connected to the top, like you have a column, okay? That's not always the case. You might have a layer that is disconnected from the surface, and then under that layer, who knows, it might be overpressure, it might be under pressure, and you find out when you drill. So, there could be all kinds of things if you're actually disconnected from the surface. But there's also just the rock, and rock in itself is rock plus fluid system. That stress is going as 1 psi per foot, or 23 megapascals per kilometer. We commonly drill up to 3 kilometers, 5 kilometers even deeper. So at 3 kilometers, your stress is 69 megapascals higher than surface, which we can take. So that's a lot of stress. Temperature goes approximately 23 Celsius degrees per kilometer, give or take, with respect to what is on surface. So if surface is 30 degrees, now it's nice and balmy, 23 Celsius degrees outside as well. Then add plus 3 times that to get to 3 kilometers, and you're very close to boiling for water. Okay? So in that case, our fluids are going back and forth between being a fluid versus gas versus supercritical and so forth. Okay? So it's very important to know what the state equation of state is for something that we might regard as gas at room temperature pressure. Okay. So therefore, the final point is that petroleum fluids are complex, so you always have multiple components. So different components will do their different thing at different pressures and temperatures. So you might suddenly, out of the liquid, have both liquid and gas, right? And so forth. Or out of a gas, have both liquid and gas. So those changes happen all the time. So oftentimes, we cannot just regard those fluids as ideal gases, even if they're at room temperature they could have been. So ideal gas law is simple. It just says that the P times normalized volume is equal to R. R is a gas constant times temperature, right? So whatever you give me in that equation, P, V, or T, I know how to, so I need two and I'll know the third, okay? Easy to compute. So that's for ideal gas law, except that most of the fluids we're dealing with are very far from ideal. So in that case, I have Pegg-Robinson, and Pegg-Robinson is this nonlinear equation. It tells me that pressure, I still have P, V, T, there's also V, V, and then there's this A, B, and R. And great, given the fluid like or gas like methane, I know what A is, I know what B is, these things are tabulated. R is still a gas constant, but just because I know all of the numbers and you give me two, that doesn't mean that I can compute the third easily. If the two you give me are volume and temperature, great, I can figure out pressure. But if the two you give me are pressure and temperature, what is volume? Kind of a little complicated to figure out. And technically, there is no analytical way to compute that. And when there's no analytical way, so for given pressure, this equation works for pressure in bars and temperature in kelvins. So if you give me P of 50 bar and T of 473 K, I can plug that in, but I can't just compute what VI is, what is the volume. Okay. In that case, I need a numerical method. I don't have an analytical formula that actually gives me the result. So what we are going to do over the course of this lecture, we're going to learn simply a general way how to set up this problem as a so-called root-finding problem. And for that general setup, we will have a number of numerical methods that we can track. So mathematically, what we're going to do, we're going to take whatever, this is equation that is describing our physical problem. There could be different way to express that equation. We're going to always, if I'm looking for volume, I'm going to set it up as a function of volume is equal to 0. So I'm going to algebraically rearrange this so that it becomes a function of volume equals to 0. And here I simply, if I put in 50 inside pressure, okay, I place this 50 here and everything that I know here, and I just basically put everything that is on the right-hand side onto the left and say it equals to 0. That's essentially my function of volume equals to 0. So whenever I'm setting up to use or to solve something as a root-finding problem, this is what I do. So function of whatever it is I'm looking for equals to 0. And then we're ready. And we'll see how do we then solve problems. And it could be V, it could be X, it could be whatever it is that I'm looking for, and however I want to name that variable. Great. So this is my function. It looks ugly, but we will figure out what are the ways to actually solve that. Let me give you another problem. There's another one, is the falling parachutist. So if I kind of know all of the physical laws. So typically we start from some physical laws that we know about the problem. So if I have a parachute that is falling down, I know that there's mass times acceleration, meaning gravity pulling it down. And that acceleration is what I'm typically looking for in some problems. But here, it's actually, if I'm actually watching an experiment, I can actually see the person fall and measure that acceleration as well as the velocity, right? So that's something I can measure. I know the mass of the entire system. Now my force balance, once the parachute opens, okay, and starts going steadily without acceleration, that's where I have a force balance. Okay? So I initially start accelerating. Has anybody jumped out of the plane? Kind of fun, right? So if that parachute opens, I mean.
Okay, so once it's open, if there's a hole in it, then we have a problem. Other than that, when it opens, I have a force balance. And at that point, right, I know that basically my mass times acceleration equals to gravity that is pulling the parachute is down, and whatever drag force or basically resistance that I have. And the whole shape of the parachute, our shape is not enough. The shape of our parachute is basically designed to provide the most resistance. So if I was an engineer who was solving for the best parachute or trying to optimize the parachute, I would go and do a bunch of these tests and see how the shape, a number of stripes, you name it, of this parachute actually gives me the best resistance. Now, what do I know about the resistance? It's basically some coefficient that is called drag coefficient that I have for some very nice bodies like spheres and so forth, but I don't have for these complex shaped parachutes, and I essentially need to test. Okay? So in that sense, my velocity, I can actually set up the equation and integrate it. Okay? And technically, what I'm solving for here is the drag coefficient for the given type of the parachute that I'm working on.
So the drag coefficient is the C.
It's C, right? And that's something, again, I don't know. For a general complex shape like that, that's not something that I have a formula for, so I'm typically looking for it. So if I was an engineer trying to optimize it, I would basically solve this for C a lot of times. However, the equation itself is nonlinear, so I can't just easily pull out C equals to something, right? And this is, again, one of the problems. So this is what my physical laws are giving me, that when I integrate this equation, I get V of t is equal to gm divided by c times 1 minus e to the minus c over mt. Okay? And everything else, so what is c if I know what gravity is, I know what mass is. Velocity is something that I measure as I'm doing the test. And time, again, is something that I have or I'm looking for. Great. So then I rearrange this equation, and I get that f of c is something like this. Basically, this is my 40 here. And whether I decide to call this f this minus this equals to 0, or this minus this equals to 0, same thing, right? 0 doesn't care for the sign. So this is my function. So let's actually try to figure out how to solve this. So we need to come up with some sort of an algorithm that will iterate step by step, and in every step try to get closer and closer to the solution. So what would you first do if I just give you, hey, find me C there?
Add 40.
Add 40? Well, like you just have this function. What would you do? How would you find C? Something simple. You have a calculator. What would you do? Punch in a number. Throw in a tens, 20, 30. Test it a couple of times. Okay. Now, if you actually have Python and you went through the lecture 2 that we went to, what would you do?
Error.
Make loop to plot. How about plotting? Right. So instead of just punching, so if you had just had a calculator, punch in a bunch of numbers, okay? And try to gauge, where is this function? I need a 0. Where is this function positive? Where is this function negative? Can I get closer to the point? Right? So, great. So that's already a great lead towards an algorithm. We just have to make it a little more systematic. So let's see if I plot this. Okay. I will actually get something like this. Okay. And now I guessed here 0 to 20. If I knew a little bit of something about drag coefficients, they're positive. Okay. This is the way they're set up. They're positive. So I start punching in. I don't know the magnitude, but you try out. And on 0 to 20, this is what you get. Let's do that. Let's open up our Python. or Jupyter Notebook. And this is basically the result that you would get if you were just having your calculator on you. But I'm going to open a new one. And I'm going to call it Lecture5 RootFinding. And I'm going to say Spring2019. So this is my f of c. I'm going to define f of c. And that is, now it's just about typing it correctly. I'm going to call the result FC. I like NumPy. I'm going to work with NumPy. Though there's exponential function you can probably find in multiple other. So I define the function that basically computes this. What do I need to do for this function to be complete or correctly defined? Great. So now I actually want to plot this on 0, 20, for instance, right? So I'm going to give myself a range of C's. What is the best way to do that? That works. Linspace works. However many in between, as long as I get range. So will this function work if I just throw in entire vector C array? It's going to work on entire vector. Shall we just try? Any other bets? Is it working on the entire vector? What's the problem? Ah. 8 doesn't like 0. Sure. Seems to have computed something. I don't know that I have the correct range of numbers. That's my problem here. This is my problem. Ah, that's a little better. So it actually does work. I can divide by entire vector. It's going to figure out this point by point. If in doubt, do a for loop and compute all of these one by one, right? So now I'm going to plot. What do I need for plotting? I lost my ability to type over spring break. except that I've been typing entire spring break. CFC, what's spring break? CFC. So this is just a basic plot. And of course I need to execute twice. Well, for one thing, it does look close to whatever I had on the slides, so that's the first check. And I also kind of want to find where it's zero, so I'm going to actually plot zeros of the same size as C. It's a nice little trick. C and NP zeros of C shape. So when I do that, I'm going to get the second line to see where they actually intersect. Yeah? Oh! Excuse me. And now all of the onslaught will shush. Sorry about that. And of course it's span. What else would it be? Okay. Here you go. Everybody got it? So technically, now I can see that there is indeed, I'm intersecting 0. So on this interval between 0 and 20, I can find where this function is 0. If I zoom in, well, it's somewhere here between 14.5 and 15, right? And I can zoom in and zoom in and zoom in with this plot to actually see where that is. That's called basically graphical inspection. And overall, it works for quick visual check. Okay? I can see the range, I can kind of zoom in and get better and better and better, but I need a number, I need a function just to give me a number. So what would you think would be a good way just to systematically get closer to this number? I start from, for instance, 0, 20. How do I systematically get closer and closer and closer to zoom in here? Limit by computer cop. Right? So something a little more practical. Yes, you could go analytically at it, but if I have a computer, how do I make this to a half smaller interval that is closer to this?
Change your lens space.
I could change my lens space. So essentially, here's one system. I can say, hey you, divide this in half. So 10 is my half, right? And then check, hey, is there a way for me to check whether this half is the interval or whether this half is the interval? And throw away the one that is not. And keep 10 to 20, and then keep going. Right? What would be this way to check whether this is the interval? For loop? Sure, I'll do that in a loop, no doubt about it. But what is the check whether my interval is good or not?
If statement. If statement.
If statement, if what? What is the key thing? So I'm crossing a 0. What happens when I'm crossing the 0 in a continuous way? I go from positive values to negative, or the other way around. So if I have a root somewhere in here, that means that on one end of the interval, I'm going to have a positive value. And on other end of the interval, I'm going to have a negative. At least this function that I plotted right here. It's not always that simple. Right? So what is that if statement going to say? If f of one end times f of the other end is negative, right? Because positive times negative will be negative. So that's negative, that's the one to keep. Yes? Now we just have to write that up as an algorithm. What I have described is it's systematic, right? You can tell, hey, give me a midpoint here. 0 plus 20 divided by 2. And then now inspect this interval and this interval, make a decision, move on. Yeah? And just keep doing that until when? We gotta always stop somehow. I don't know how long I'll go, so I'm gonna use a while loop when I don't know how long I'll go. But when will I stop? What is close enough? What is good enough for finding a root? Who knows? I decide. Okay? So I decide what is close enough. And as an engineer, I have some idea about that problem, right? So for instance, if I'm measuring mass, okay, depending on the problem and how sensitive the problem is, I can say, well, if this is a problem of mass, then when you're less than 1 milligram, because 1 milligram is the best I can do with my scale to measure anyway, then that's good enough. Okay? If I don't know, then I just do an educated guess. Okay? For drag coefficients, I don't know, but I'd say down to 0.001, and that should be fine. Okay? If these are 15 of something, then 0.001 is probably all right. Okay? But again, I decide, and sometimes I have a good idea as an engineer what should be the stopping limit, and sometimes I just kind of go with some bad. All right, so let's formalize that. I'm going to first walk through the slides, and we're going to formalize it better. So again, if I was just alone with my calculator, I would try a bunch of values, right? And then I would just type in. So these are just the values that are here circled. So you have 34, then you have 17, 6 minus 2. So you say, haha, this is where I'm crossing 0. So I'm somewhere between 12 and 16. So that's if you just do it. And then you can just say, okay, evaluate 14 in between here and figure out which one is positive. What is f of 14? I can actually right now calculate. You can calculate what is f of 14. And then see, so here the plot should give me f of 14 is still positive. 14, 16, so then this is the interval to keep and this one I throw away. Okay? So that's how I go. So let's actually see this. Okay? So my test, basically if I have a continuous function on some interval and I have a lower and upper limit of that interval, then basically if f of xl times f of xu is less than 0, I should be crossing a 0 somewhere in between, right? So let's formalize that. Basically, I need two starting values, so 0, 20 or 12, 16, both work here. And then I bisect this in half, so I find the midpoint. That's what it means to bisect. And then I look at f of 14. So if f of 14 times f of 16 is less than 0, that's the interval to keep. Right? So I'm just going to update my lower bound value to be this 14 and not 12 anymore. Yes? So now I have my XL to be 14 and XU remains at 16. Otherwise, if actually this was the interval to keep, then I would say, okay, my upper bound is not 16, but it's 14 now. Yes? So my basically check with if statement, somebody mentioned an if statement, will be like this. If f of, I should have called this L, this is my, so I'm going to call this midpoint XR. And I'm going to calculate f of this midpoint. And then if f of xr times f of xu is less than 0,
I'm going to either replace the lower or upper bound, depending on which of these cases is true. And I'm going to keep going, okay, until the difference between these two values, upper and lower, is less than some number that I want. Lots of hand waving. Let's apply. So essentially, I'm going to say, let's start here. So let's start with 12 and 16. So I'm going to say XL is equal to 12 and XU is equal to 16. So this is what I call, by visual inspection, I take interval 12, 16 as a starting, I call that bracket. We need to bracket the root. And visual inspection is just from plotting this. Great. So now I'm going to say while XLU minus XL is larger than, I'm going to stick with 0.001, it's just fine. What will I do? Find a midpoint. So XR is XL plus XU divided by 2. Then test which subinterval to keep. This is, hey, if f of xr, this midpoint, times f of xu is larger than 0. So let's just quickly look at my slides again. So, okay, so here I am, this is my midpoint. If f of xr times f of xu is less than 0, as it is in this case, then I want this lower bound, which used to be 12, to become this newer lower bound, which is xr. So all I'm going to say is, well, xl is now xr, and xu remains the same. So that basically, my new interval becomes xr, xu. Otherwise, if I was actually, so in the next step, when I divide between 14 and 16, I'm going to look at 15, and 15, it's going to be 14, 15 that is my new interval. So I'm going to say else if, elif, f of xl times f of xr is less than 0. Then this new upper bound becomes xr. And the lower bound stays where it is, right? So lower bound stays where it is, and my upper bound becomes, my new interval becomes xlxr. Okay, great. Else, now what's the case if none of this is true, then it's actually 0. So I have hit somehow xr as the 0. That's gonna be pretty rare, but I can just say then, okay, both my XR, XL is XR, and XU is XR because it appears that magically I have hit 0. And I should go play lottery. I have magically managed to hit the 0. Okay? So this will basically stop my algorithm because both the brackets will become that number. Ready to try it out? So what I'm going to print at the end of this is XL, XU, and then equals to, or just X, how about this? XL equals to XL. And then some space, XU equals to, and XU. So it appears that my root is somewhere between 14.7792 blah blah and 14.78, right? And the difference between the two is obviously less than 0.01. Which one is the root? All I know is that root is in there. So whichever of these numbers I take as the root, my accuracy is within 0.001 of that root. Yes? Cool. We've solved this problem. Now what I'd like to do, since I would like to use this often, okay, I'd like to make a function out of it. How are we going to do that? So I'm going to say, hey, I'm actually going to just copy everything here and make a function out of it below. So I'm going to say, hey, let user suggest what XL and XU should be. I'm going to say define bisection XL, XU. And the only thing that I need to do is actually return those values or return new values, right? So basically what I'm returning is return updated values. I could also simply return XR. How's that? Let's just return XR, and that's my estimate of the root, one value. Though I technically know that all I know about this root is that it's somewhere in between those two values.
Could you just
Mm-hmm. So I just took my code and wrapped it up in a function. And now I'm just going to be able to estimate, use this code. So I can say bisection 1416 and XR. Or I could say XR bisection 020. So let's see what do we get when we execute with two different endpoints. Well, I messed up indentation. I thought I indented it. Ah,
All of this needs to be indented. Yep. So you can see that with slightly different starting points, I'm going to get slightly different result. And that's okay because I'm looking for the 0 with 0.001 accuracy. Okay? So yes, you're going to get slightly different results with slightly different input, and that's essentially how these things work. Did everybody get a working function? Great. So now I can actually use this code and find a lot of different things. So I could basically just take the code and change up the function. And I will repeat the process. Okay? So my slides here seem to suggest. So did everybody work out the code? So my slides suggest an alternative function. And every function will be slightly different. Okay? So what I want you to do by Wednesday is I want you to take this alternative function here and go through the process for that function. And the key here will be, basically you just adapt the code. The key here will be that you have to go and plot the function. It's a different function, so it's going to have slightly different range. 0, 20 might work for it or might not. You'll have to do a little bit of trial and error. And another thing that can happen is that that function might not, here we kind of zoomed in and we didn't plot anything else. Right? If I enlarge this range, let's say that I go to 200 to plot this, it seems that I just keep going negative. So this particular function, in the positive, physically relevant values, which are positive for drag coefficient, it really has only one 0. Okay? But if I have multiple ones, multiple zeros, I have to then decide which one am I going to find. Okay? And my different choices of intervals might zoom in on a different value. Okay? So you can play with that a little. But you have to understand that you're going to find basically only one root that you have bracketed. Okay? But if there are possibly multiple roots within that bracket, which one you're going to find kind of depends on a little bit of like what is this test that it's checking. Okay? So that's something to play with. So there's something that says something about root finding. There's never just like, oh yeah, I'm just going to plug in the values for either this XL and XU and everything is going to work fine. You kind of actually have to often play with it a little and know your function, because with the different function, especially when they get non-linear, or maybe start changing really rapidly, then it's kind of really hard to know when it is, what choices to make to actually have a robust outcome. So again, please do that for the next time, and Ningyu will set up online quiz thingy for that code. So again, by Wednesday in class is just fine, and the function is this one over here. Yeah? Slide 12. Okay? All right. I think that's a great point to stop for today.